Next up, we have Nandor Leaker, who will present Duplo, a framework for OCaml post-link optimization.
Hello, my name is Nando Liker, and today I am going to talk about Duplo, a framework for OCaml post-link optimization I built with Dr. Tim Jones at the University of Cambridge. Why build a post-link optimizer, and why build one for OCaml in particular? OCaml is a high-level language, which means that it is not well suited for expressing specific low-level constructs. As an example, we consider a simple type to represent complex numbers composed of an imaginary and a real component. If we declare a complex number as a pair of floats, we end up with many allocations. Even though we only care about 8 bytes of data to store two 32-bit floats, the object will be spread across 56 bytes and 3 distinct allocations, producing 3 distinct blocks on the heap. Ideally, we like a single block with a header and 8 bytes of data. So how do we get there? We can write a lot of code, possibly filling with bits, and express the type in OCaml. However, the solution is unlikely to be elegant. We could also change the runtime or the compiler. However, this is not practical nor scalable and could become a maintenance nightmare. We choose to instead use an existing language feature, namely the foreign function interface. The FFI allows us to use the right tool for the right job. We can express low-level constructs in C and call them from OCaml. The FFI of OCaml is particularly powerful thanks to its minimal runtime and simple object representation. This allows us to read arbitrary objects from the OCaml heap and also to allocate arbitrary objects on the OCaml heap. Such features allow the FFI to be flexible enough to build a wide variety of types and functions. However, the FFI does not come for free. Besides the implicit trampolines and heap root management code required to invoke C from OCaml, we pay the cost of missed optimization opportunities. In a typical build, OCaml and C meet in assembly form in the linker. Unfortunately, high-level transformations of machine code are far from trivial. We need a common form more suitable for analysis. Ideally, a representation that has not yet gone through register allocation nor instruction selection. So, the goal of Duplo is to ameliorate this FFI overhead. And to reduce the overhead, we want to optimize across the language boundary. However, on one side we have OCaml and C on the other, two very different languages with different memory models and different runtimes. In order to apply any optimizations, we need to first find a common denominator capable of capturing the semantics of both C and OCaml. Duplo achieves this with a representation we call LLIR, Low-Level Intermediate Representation. The framework provides a custom version of Clang to lower C to LLIR, a custom version of the OCaml compiler to lower OCaml to LLIR, and an entire toolchain to link LLIR modules into a single module containing whole program information. And finally, an optimizer, which we call LLIR opt, to analyze and transform the program before lowering it to executable machine code. LLIR is the central component of our project. It is built to be easy to optimize. It is in SSA form, has virtual registers, simple instructions, and primitive types with direct hardware equivalents. Even though it is not LLVMIR, its in-memory representation in C++ is almost identical to LLVMIR, mirroring several useful methods and reusing support libraries, including valuable functions and iterators, such as dominator tree construction and post-order traversals. We find the code style of our transformations to be quite similar to that of LLVM, and this familiarity is highly valuable. Despite some similarities, LLVM is definitely not LLVMIR. It is less abstract and a lot closer to hardware. Why is LLIR low level? This choice is almost entirely constrained by the OCaml compiler and the intermediate representations found in Clang. OCaml first compiles to lambda form with closures which have no direct equivalent in LLVM, require us to step one level down in the OCaml compiler. The next step is CMM, which still has some high-level features, so we need to go down another level. We are left with building LLIR from Mach linear, which are essentially equivalent to machine code. LLVMIR is more abstract than that. We need to lower it a bit in LLVM. Conveniently, we defined LLIR to be almost like machine code. We lower LLVM-IR to LLIR through the target-specific backend of LLVM, passing through selection DAG and LLIR-specific machine IR. On the OCaml side, we generate LLIR from linear, as the mapping is almost one-to-one. We are essentially cross-compiling to a new target in both compilers. Getting to LLIR is only the start of the journey. We also need to generate machine code from LLIR, and this step is non-trivial. Code generators tend to be complex pieces of code, and OCaml has the runtime and the garbage collector that we do not wish to alter that imposes further constraints. Since our toolchain already includes Clang, we decided to use the LLVM code generator from its selection DAG representation onwards. We have added a custom instruction required by the OCaml GC, using the entirety of the target-specific machine IR pipeline. Since we cross-compile C to LLIR, we have a mapping from selection DAG to LLIR. In our backend, we map LLIR to selection DAG. Due to this circular dependency, most of the LLIR instructions have a direct correspondent in selection DAG, with the exception of some more complex constructs such as function calls and AT-bit floats. Simpler instructions such as add, subtract, multiply, and so on do not really warrant a custom mapping from selection DAG to LLIR nor from LLIR to selection DAG. So we simply map selection DAG to an LLIR instruction and map the DLIR instruction back to selection DAG. But function calls are specific to each target, and even in all of LLVM's backends, they require custom mapping from LLVMIR to selection DAG, and we have that mapping for LLIR as well. And because of these constraints, we actually had very little freedom when designing our new representation. Probably the most pressing question is why not lower to LLVMIR? Previous attempts made some progress, albeit with the runtime cost. OCaml is not an easy language to map to LLVM. Its exception handling requires explicit stack manipulation. OCaml also lacks a shadow stack for root pointers. This aspect is crucial for performance. While LLVM offers some support for garbage collectors, it does not cater specifically to the needs of OCaml. Through Duplo, we made significant progress though. We have added the required instruction to a significant portion of the target specific pipeline in order to handle the frame tables used by the default OCaml garbage collector and runtime. However, to achieve the same at the LLVM IR level, extensive changes are required. To illustrate LLIR, we can look at a simple method in LLIR form, which computes the magnitude of a vector allocated on the OCaml heap. It reads an argument, a pointer to a pair, using an arg instruction. Individual elements are loaded using LD from offsets computed using basic pointer arithmetic. The elements are squared using the multiply instruction, then passed on to the squared function before being boxed into a heap allocated block. We can notice the annotations. The OCaml runtime requires us to identify all heap pointers, which we do using camel value, and emit frame tables describing those which are live across call size that can allocate, all marked through camel frame. Finding a common representation is only part of the problem. In this representation, optimizations opportunities to perform optimizations should be scarce. OCaml should have already optimized everything. LLVM should have also optimized everything. And we are left with the non-trivial task of identifying optimization opportunities that are exposed only when both OCaml and C sources are present. Naturally, the first step is to create optimization opportunities for other steps. Inlining achieves this. Unfortunately, inlining in this context is not as simple as copying a body into a callee. The world is split into two realms, OCaml and C. The two communicate through a trampoline, recording vital information for the runtime. When we inline C into OCaml, we actually create a bigger OCaml function and push the trampolines down. Even though G initially called F without a trampoline, after inlining it requires one. H cannot allocate, thus it does not need one. In camel FF, we are left with a mess. The function now tracks heap roots using both camel values and an explicit root management mechanism specific to C. In the future, we aim to address this problem by moving roots over to the camel value mechanism. This is a great improvement since it eliminates the upfront cost of root management that's necessary in C. As you have global information, in the future we will also be able to move C functions which allocate over to the OCaml realm, further simplifying manual root management and possibly ending up only using camel value annotations to identify roots. While we are not there yet, at some point we will be able to not care about whether a function is OCaml specific or C specific, erasing the boundary between the two heaps. To illustrate some more problems, we consider a function that increments a double, unboxing a value, adding one to it, and boxing it back, sending it back to the OCaml heap. After inlining, we see that the boxing camel copy double call is now annotated and it has a trampoline. But what happens if we inline two consecutive invocations? Unfortunately, we get a chain of boxing unboxing steps. This is expected and quite unfortunate. We are now faced with the non-trivial task of understanding pointers and blocks on the heap to perform even a simple transformation such as constant propagation. And the stage we are at in the pipeline does not help. The common ground between C and OCaml memory representations is not particularly verbose. We can work only with the assumption that pointers are stored at addresses aligned to 8 bytes. We essentially have no type information. And even if we had type information, due to the fact that C has unions, the type information we could possibly keep would be minimal, and the only piece of information we'll be left with is this fact that pointers are aligned to 8 bytes, which allows us to model the heap as bags of pointers aligned at specific addresses. As a proof of concept, we have built two transformations working with pointers: a local analysis to propagate values stored to memory to loads reading them, and a global analysis to identify indirect call targets essential for that code elimination. Presently, our optimizer implements a number of classic transformations, which are required mostly to eliminate inefficiencies in the C OCaml LLIR lowering. While we have exposed many new opportunities, our goal for the moment was to implement the minimal battery of transformations required to emit code as fast as, well, at least as fast as it was emitted by OCaml and C previously. Our transformations include sparse conditional constant propagation, unreachable code elimination, and control flow simplification. And these are scheduled after inlining and simplify the program quite a bit. Their recursion elimination is vital. LLVM cannot lower direct air recursion as effectively as OCaml, but it generates identical code if these functions are turned into loops instead. An interesting transformation specific to this context is trampoline elimination. OCaml requires a trampoline to switch from the OCaml calling convention to the C calling convention when invoking a C method indirectly. Since we have global information, we can change the calling convention of the C method to the OCaml one, completely eliminating these trampolines. These transformations, along with the LLVM code generator, provide some benefit. We benchmarked our optimizer on a subset of benchmark from OPERF macro and OPERF micro. Unfortunately, we do not yet implement some optimizations performed by the OCaml compiler, which we have disabled in our reference version. We do not cache some globals in registers, and we do not inline allocations. Despite these mitigations, the relative results should still be relevant. Our linker delivers a significant reduction in code size, while LLVM manages to select better instructions, providing some improvement on large informations, and we're quite happy about these results. When comparing the effect of the small set of transformations we have implemented, the effect is moderate. There are not many opportunities for cross-language optimization, as our inlining heuristics and poist analysis are quite primitive. As an example, we currently inline aggressively functions which box or deconstruct arguments in the hope of propagating constants through them. In the future, we have to build better heuristics to base our inlining decision on. However, for the purpose of this project, the difficulty was in figuring out how to do inlining in the first place. We do gain in performance a bit by mitigating inefficiencies in both backends and inlining some small methods through the battery of transformations we have presented earlier. To sum up, we have presented a Duplo framework to inline C into OCaml, analyzing and transforming the resulting code. We built a new representation to capture both OCaml and C, and which we call LLIR. Finally, as our code generator, we have shown how OCaml can be lowered to part of the LLVM pipeline, yielding an improvement in code size and performance.
Thanks very much, Nandor, who's now available in the New York time band for question and answer. You can click the link in Clowder.